Okay, class, good afternoon. So this is the third topic in the processes of ideal gases. So this is constant temperature process. So this is the first presentation of this topic, class. Okay. So this presentation shows how the formulas uh, determining the PBT relations, the heat transferred, and so on and so forth was derived. Okay? So, for constant temperature, the value of N is equals to 1. Okay? So, from the equation PB raised to N is equals to constant, if N is equals to 1, PB raised to 1 is equals to constant, or PB is equals to constant. Okay? So, meaning from first state point to the other state point, the product of the pressure and volume is considered constant. Okay? So, let us consider this illustration in this slide. So, we have here from 1 to 2, the curve from PB diagram. Okay? So, the curve from 1 to 2, below is, of course, the work non-flow. Okay? Work non-flow. Okay? So, for TS diagram, below the curve 1 to 2 is the heat transferred. Okay? So, take note that we have also here the illustration for constant temperature process. So, the piston. Okay? For constant temperature process. Okay? So, for PBT relation, or the relation of the pressure, volume, and temperature, from the ideal gas equation, PB is equals to MRT. So, do not forget this equation. So, even if the processes proceeds to isentropics, to polytropics, still, this equation is always needed. Okay. So, from the combined ideal gas equation, P1, B1 over T1 is equals to P sub 2, B sub 2 over T sub 2. Since T sub 1 is equals to T sub 2, we can eliminate T1 and T sub 2 from this equation. So, therefore, the equation now is P sub 1, B sub 1 is equals to P sub 2, B sub 2 is equals to constant. So, where, of course, P sub 1 and P sub 2, that is the absolute pressure from the initial to final state points. Okay? And B sub 1 and B sub 2 is the initial and final volume of the gas. Okay? So, another is the work non-flow. Okay? So, take note that the work non-flow is equal to the area below the PB diagram. Or simply, so by taking the differential strip below, so that is work non-flow is equals to the integral of P dB limit from 1 to 2. Okay? But for P is equals to C over B, and then substituting the value of P, which is C over B from the equation, work non-flow now is equals to the integral of C over B dB. Okay? Limit from 1 to 2. Okay? So, therefore, putting now the constant outside the integral sign. Okay? So, bringing the constant outside the integral sign, that work non-flow na is equals to C integral of dB over B limit from 1 to 2. So, we know already that the integral of dB over B is equal to the natural logarithm, of course, of the volume of the higher volume to the lower value of the volume. To eliminate, of course, the negative value of the answer. Okay? So, but also, that W or work non-flow is equals to C ln of B over B sub 2 over B sub 1. So, applying the limit now. But C is equals to P1 B1 is also equal to P2 B2. Or say, work non-flow is equals to P sub 1 B sub 1 ln of B sub 2 over B sub 1. But there is also a variance for this equation. Okay? So, here is now the variation. PB is also equal to MRT from ideal gas equation or the equation of state. Okay? Is equals to, or the work non-flow now, is equals to MRT ln of B sub 2 over B sub 1. Okay? But, since PB is also constant, we can also replace, instead of P sub 1, we use P sub 2 and B sub 2. So, therefore, work non-flow is equals to P2, B2 ln of B sub 2 over B sub 1. And also, PB is equals to MRT also at 2. P2, B2 is equals to MRT sub 2. So, we can also replace P2, B2. So, that is work non-flow is equals to MRT sub 2 ln of B sub 2 and B sub 1. Okay, so you can use any of the formulas derived in this slide. Okay, so to make it easier for you. Okay, so another, we have the heat transferred. So as mentioned a while ago, that the heat transferred is equals to the area under the T is diagram. Okay? So, where Q now is equals to the integral of T multiplied by the change in entropy. So, limit from 1 to 2. Okay? So, take note, class. This topic is a constant temperature process. So, using now the first corollary of the first law applied to closed system where Q is equals to delta U plus work non-flow. And knowing that delta U is a function of the change in temperature, or simply delta U is equals to mCB delta T, but delta T is equals to 0. So, therefore, delta U is also 0. Therefore, the heat transferred now, class, is equals to the work non-flow. Okay? So, where the work non-flow, you can use any of the formulas in the previous slides. Okay? So, also, heat transferred. So, from the previous slides, Q is equals to P1, B1, ln of B sub 2. Q is equals to MR, T sub 1, ln of B sub 2 over B sub 1. And then, Q is equals to P2, B2, ln of B sub 2 over B sub 2. Or Q is equals to MR, T sub 2, ln of B sub 2. But you can also, class, use the ratio of the pressure. Instead of B sub 2 and B sub 1, you can also use the ratio of the absolute pressure. Okay? If pressures are given, you replace the ratio of the volume with the ratio of the absolute pressure. Okay? So, another class. So, change in internal energy. So, take note that if delta T is 0, of course, delta U is 0 because delta U is always equals to mCB delta T. Okay? So, that is why delta U is 0 here. So, if you are given, of course, with problem, solving for delta U or looking for the value of delta U, you simply answer delta U equals to 0 since delta T is equals to 0. Okay? So, it is clear, class, that the value of delta U is 0 for delta T equals to 0. Okay? Another, we have the change in enthalpy. Another, this is a function of the temperature also. Okay? Delta H is equal to mCp delta T. But delta T is 0 for T equals to constant. Delta H also is equals to 0. Okay? So, take note, class, that delta U and delta H for T is equals to constant are all 0. Okay? Another, we have here the change in entropy. So, knowing that the change in entropy, delta S is equals to the integral of dq over T. Limit are, yes, limit from 1 to 2. So, knowing that dq is equals to mr T sub 1 ln of b sub 2 over b sub 1. Okay? So, over T sub 1. Okay? So, delta S now is equals to mr ln of b sub 2 over b sub 1 equals to mr ln of p sub 1 over p sub 2. Okay? So, very simple. Okay. Another is the steady flow work. Okay, so take note that the steady flow work is equal to the area behind the PB diagram. Okay, so taking now a differential strip from the PB diagram. Okay, work steady flow now is equals to the negative integral of B dP. So, limit from 1 to 2. So, for PB equals to C, B is equals to C over P. So, substituting now the value of B, which is equals to C over P multiplied by dP. Okay? So, take note. So, putting up na or bringing the constant outside the integral sign. So, that will now become work steady flow is equals to the integral or equal to P sub 1, B sub 1, the natural logarithm of P sub 1 over P sub 2 or MR T sub 1 ln of P sub 1 over P sub 2 or P sub 2 B sub 2 ln of P sub 1 over P sub 2. Okay? Or MR T sub 2 ln of P sub 1 P sub. So, take note, class, that there are so many variation and computing the steady flow work, okay, of course the isothermal process. Okay, so also, okay, so that ends now my presentation, class. Thank you very much.